So in continuation with the LPP problem, we are going to see one sample case. This is about Marina Mines. Instead of looking at all this question, I'll just explain it briefly through Excel. So Marina Mines is a mining company. They have four mines: Mine 1, Mine 2, Mine 3, and Mine 4. In Mine 1, pure iron content is 70%. It is if they extract say 100 tons of ore. So in mines we extract ore. In that the iron content is 70%. 70% is 70 tons of pure iron is extracted. Similarly 60% for Mine 2, 50% for Mine 3 and 30% for Mine 4. And they have given us the cost to extract 1 ton. For Mine 1 the cost to extract 1 ton is 37. This cost is extracting the ore, not pure iron. For extracting the ore 37, 46, 50, and 42. Then they have given the capacity, the maximum capacity which can be extracted. This is also for the ore. So that is 350, 530, 16, and 449, 490. So 1980 is the total capacity of ore you can extract from mine 1, mine 2, mine 3, and mine 4 combined. But when you take the purity, you don't know how much pure iron can be obtained. So how will you get it? Capacity into 70%. E3, which is nothing but 350 into 70. So you can see the formula. So this 70% into 30 will give you this. So in the similar way, we calculated the pure capacity from all the four mines. Total you can extract 1015 or 1015 tons of pure iron. Now in the demand side, if we see, we have three customers, A, B, and C, Armco, Best, and Corcon. The demand is 400 tons, 250, 290. So this tonnage is pure iron, not ore. They want 100% pure iron. So if you see the entire demand, it is 940 and the entire supply is 1015. 1015 is your supply because 1015 is your pure capacity. In the question, we are given until this part and the demand. So we then have to calculate the pure capacity so that even if it is possible or not to check theoretically, since you have more iron, you can supply the demand. So what is the objective here? We are trying to extract iron from four different mines. We want to know how much, means how many tons of iron ore should be extracted from each of this so that the cost to extract is less and the same time the demand is satisfied and the capacity is not omitted. Means we are not going beyond the capacity. So number one is to minimize the cost. Have to reduce the cost to extract the iron. Then number two, to meet the demand. Then number three, to limit within the capacity for each mine. So you're not exceeding the capacity. So these are the three major things you have to remember before jumping into this. In similar way, we'll just start constructing the LPP. So again, mine 1, mine 2, mine 3, and mine 4. So now, if you see the coefficients, these are the cost coefficients. 37, 46, 50, and 42. The same values are entered here. And this is 0, 0, 0. I'll just do it again. I have solved it previously. 0, 0, 0, and 0. Every value is 0 right now. We don't know. This is value is how many tons are to be extracted from each mine. Then what is your objective function? This is your cost, total cost of extraction. Number of tons into cost to extract. Then what is the capacity? For the mine 1, the capacity should be less than 350. We are using the 100 model. How? Suppose, let us assume that M1 is the number of tons of ore which is extracted from mine 1. Similarly, M2, M3, and M4 respectively from the different mines. What are the constraints? M1 should be the total which is being extracted is less than or equal to the capacity. Capacity given is 350. Is that So how do you satisfy the demand? Instead of just going for the individual demand from entire customers, you have to go for the total demand. Why are we going for total demand is we are the only supplier here. We have three different customers. So if we are the only supplier, we can extract the ore from any mine we want. The customers are not demanding that they want from a particular mine. They are only worried about the purity. So if we are able to supply 940 tons, we can distribute it accordingly between the customers. That's why. And then if you see the purity part, only 70% of ore from mine one is pure. The customers want 100% pure quantity. So total iron which is extracted is 0.7 into M1 plus 0.6 into M2 plus 0.5 into M3 plus 0.3 into M4. So this value is the total iron. It is pure iron. Why pure iron? Because we have multiplied the purity. We have multiplied into purities. This is the number of ores, tonnage number, count of the ore, and this is the purity. When you multiplied it, so this value gives the total tonnage of pure iron extracted from mine 1. Similarly, from mine 2 and mine 3 and mine 4. This value should be equal to 940. Why 940? 940 is your total demand. Why equal to? One thing is, if it is less, then you can't satisfy the demand. If it is more, then the cost for you will be high, which means you are incurring more cost, which is wastage. So we are equating it so that the extraction is equal to demand and you are optimal in cost. So these are the values which we have put it in the constraint. Then you can see the LHS is the same, which is the sum product of the values. We have already done it. So all the constraint less than equal to, this is the RHS with the capacity, and this is 940. So then just let us go to solver, data, solver. Then let me just reset this. So your objective function z value is here. You selected it. Then you are minimizing the cost by changing the variables. These four are your variables. Then you have to give your constraints. So add them. The 3 less than or equal to capacity. Then the demand constraint. And be careful with the equation symbols. Okay. Simplex LP, then solve. And solve and just generate these reports. Since I have already generated the reports, I'm here, but you just generate them. Then click OK. This is the total cost of extraction. And these are the values, number of tons you have to extract. Mine 1, the entire capacity is being used. Here you can see there is no slack. This is a binding constraint. For mine 2, 530, entire capacity is used. For mine 3, entire capacity 610 is used. For mine 4, we are only extracting 240 tons, which is 490 tons is the entire capacity. So here we have some slack. We can extract some more in future if it is needed. And the 940 demand means we are the entire extraction is satisfying the demand. So the demand is satisfied, cost is reduced, capacity is satisfied. So we have successfully applied all the three restrictions which we have started with. So in this case, we have sub questions. Here they are asking, write down briefly the sensitivity report with its feasibility and optimality range. So sensitivity report we have seen yesterday itself. Z is the objective function and these values are your optimal solution. Whatever the variables we are changing, this is the optimal solution. So for this sensitivity report, just see the report. I have asked to generate. This is a sensitivity report. This is nothing but the report. We have already interpreted it in the previous video. So the above table, if you see, these are the allowable increase and decrease, and the below table you have these all the shadow prices and these values. Then they are asking it, just give the report over here. So we have just copied and pasted it with briefly write down it. Then the feasibility and optimality range. What are the ranges? What are the range when it will remain optimal? So above value, you see the coefficient is 37. So let us generate the lower limit, then upper limit. So the coefficient is 37. Allowable decrease is almost infinite value. So the lower limit is negative infinity. Then the upper limit is 37 plus 61, which is 98. Similarly for this, 46, and this is again negative infinity, and 46 plus 38 is 70, 84. This is again negative infinity because this value is very huge. Then allowable increase is 20, which is 70. Then allowable decrease is 12. So 42 minus 12 is 30. Allowable increase is infinity. So this value is infinity. So these are your ranges for which the optimal solution. But this for this range, if you are varying the coefficient, respective coefficients within the respective limit or the respective range, the optimal solution will remain the same. Otherwise, it will change. That is what we have seen in the study video. Then the Z value, we have seen also how the Z value will vary. We have said that a unit increase in the right hand side of the constraint will increase the Z value by the shadow price that we have seen. Then when we come to the B part, feasibility, we'll come back to it after some time. Which mines are bind to production? Do any mines have slack capacity? If yes, which one? The first question says, which mines are bind to production? So here I have said it earlier itself. Mine 1, entire capacity used, which is it is bind, there is no slack. Mine 2, entire capacity used, here also it is bind. So mine 3 is also binded because there is no slack. But mine 4, there is a slack. How much of slack is there? 490 minus 240 is your slack. But remember, 490 is the capacity, it is of ore capacity. That we can check it later how pure it is, but there is slack. It will come in the next question. There we can see. So here, if you see, the answer is mines 1, 2, 3 are bind to production, whereas mine 4 has slack. So that answers part B part. Then if we come to the C part, if Marina Mines, which is the company, if they could increase the production capacity at any one of the mines, which should it be? Why? What will be the implication of the optimal solution? They are asking if they increase the production capacity means what? The RHS. If they increase the RHS at any one of the mines, which one should it be? Why? What will be the implication on the optimal solution? The solution is it should be mine 1 because its cost of production is least and its iron purity is the highest. The optimal solution will further decrease when production capacity is increased at mine 1. We'll just go it slowly once again. They are asking, can, if they are increasing the RHS at any one mine, which should it be? Why? What is your logic behind it? And what will be the implication on optimal solution? Suppose if we see with the cost, why, if we are able to increase the capacity, then what will we check it? We'll check first how is the cost, then we'll check how is the purity. If you check mine 1, the cost is the least among all this, 37, 46, 50, and 42. And the purity is the highest. So this is a benefit, this is a good pair to start with. If it has not been a better value, then you have gone with another pair. But here it is a good pair. The cost of extraction is less and the purity is high. So with less extraction, you can get main benefit. So that increase in the capacity of mine 1 is profitable. That is the logic. Then they're asking what will be the implication on the optimal solution. So when you increase the RHS by the unit, then what will happen? It will increase the Z value by the shadow price. But here the shadow price is in negative. We have to just check if it is in the allowable increase or allowable decrease or not. That is to be checked. So here you have the values. The right hand side constraint. The allowable increase is 102 units, 103 almost. So it can be increased until 453. So the upper limit will be 453. The lower limit is almost 107. 107, 43 and 243. So 242 will be the lower limit. 242 point something decimal. So if the right hand side of mine 1 has been extended or is within this range, then the Z value will reduce. Z is what? Z is your total cost. Why is it reducing? It is reducing because mine 1 has 70% purity. They did not say anything about demand. The demand is still remaining the same, but you are extracting from mine 1. In that case, you will not use mine 4. Instead, you will divert the entire usage from mine 4 to mine 1 until capacity is satisfying. Because of that, the purity is high and the cost is relatively less. So the Z effectively will reduce. That is what the shadow price is also telling us. It is negative. It is saying right hand side of mine 1 is increased. We have understood why it should increase because the cost is less than the purity is high. That part is understood. Now they are asking if that is increased, what will happen to Z? What we have learned is if the value, what will be the implication of optimal solution? Optimal solution means what? These variables. These variables will definitely change. Optimal solution is saying about the variable that will definitely change. That is the part. I'm saying about objective function. Z value. Z value, how will it vary? If RHS is increased, then Z value will increases by shadow price value. But since shadow price is negative, so Z will decrease. For that, what is the logic behind Z decreasing? Since mine 4 is less pure and cost is also relatively high than mine 1, whatever we are using in this context, this 240, what we are using from mine 1, we'll divert that into mine from mine 4 to mine 1 itself. So we have to extract less content because purity is high and the cost is reduced 37. Because of that reduction, Z will fall. That is what shadow price is also saying. It will reduce by 60. So the next part, the D part. Now, if the company would like to increase the capacity simultaneously, M1 increases by 20, M2 increases by 50, M3 increases by 90, and M4 increases by 110. They are increasing four RHS capacity. Is it feasible to do? Then what is the implication? Explain and find the optimal solution. Feasible means if the solver is providing you a solution, that's all. If it is providing a solution, then it is feasible. If not, it is not feasible. Then if it is feasible, means the solver is solving. What is the implication? Implication means how are the optimal solution and how it is happening to Z. Then explain it and find the optimal cost, which is find the Z itself. So since four are changing, we don't have any theory to check it. So we are directly generating a new model. How can we do it? We are increasing the capacity. See, 350 became plus 20, 370, then 530. 530 became 580. Then the next one, 610. 610 increased by 90 became 700. Then the next value, 240, 490. 490 increased by 110, which became 600. But the demand is same. They did not say anything about demand. 940 still remains as 940. So I have already solved it. I'll just solve it again. So again, 0, 0, 0. Everything is changed. Cost is 0. LHS became 0. Everything else remains the same. They are only saying about the capacity. Since all the four are changing, we don't have any theory to directly get the value. That's why we are generating a new model again. Then we again go back to solver. And then we select the values. Reset it. So that since we are using on the same sheet, it is better to reset so that we don't get error. And this is selected, minimize the cost, changing the variables. These are your optimal solution. That is selected, adding your constraints, all the four which are less than equal with the new capacity. Then add, then this value, this is equal. We are adding symbol here in this part so that while we are adding it into the solver, we don't confuse. It will be easy to add into solver with these values. Here they don't signify anything, but while entering into solver, it will be helpful so that we don't enter wrong symbol here. Then just solve it. Solver says it is a solution is found, which means it is feasible. You can increase the capacity, you can do. Next, what is the implication? The implication is optimal solution has changed. Initial optimal solution is different. Now the optimal solution is different. Initial optimal solution is entire capacity of mine 1, 2, 3, but 4 only 240. Here, if you see, mine 1, 2, 3 entire capacity, mine 1 and 2, the capacity is entirely used. But mine 3, only 666 is required. Mine 4, we did not even start. Why? Because one, purity is less, the cost is also relatively high. So that is been avoided. And if you see the optimal cost, it is 73,000 here, it is 77,000 here. So optimal cost has reduced. So here we can add optimal cost is reduced and mine 4 is unused because the demand is remaining the same and it is satisfied with mine 1, 2, 3 itself. And mine 1 and 2 are, there is no slack, entirely used, but mine 3 has some slack. The next part, E part, if Marina were to determine that it could increase the production capacity at mine 1 from 350 to 500. So every one more part, every question when they are increasing the capacity, it is only until that part. But the other questions which are coming has to be solved from the main model itself. We should not get confused. That is remaining the same. Sub questions, the extent of those values remains within those questions. When you enter the new question is based on the main model. So then if we come back to the E part, they are saying if the company was to increase the production capacity at mine 1 from 350 to 500 at an increase in production cost to 43 per ton. Now the cost is increased and the RHS is increased. Cost is the coefficient. RHS is RHS. If they have done it separately, we have theory to check what happens to Z. But since they have done it together, we don't have any theory to suggest. That's why we are generating again a new model here. Then here if you see the cost has been updated to 43 and the capacity has also increased to 500. But if you see the capacity for 2, it is 530, not 580. Don't copy the value from D part. D part capacity is 580. But here the capacity is 530, which is as per the initial question. That is to be kept in mind. Then when that we have done, it has already been solved. So I will not solve this again because you know how to solve it. The solver is giving 73,000. You see, this value is much less. It is going on decreasing because the purity from mine 1 is high. Because of which, even though the cost is raised to 43, it is relatively the same. 43, 42, 46, and 50 are somewhat closer. Because of which the cost has reduced and you have used it full capacity. Again, mine 4 is empty. They're just asking if they should do it. They're asking the capacity if it is increased and the production cost also has increased. Should you do it or not? How can you answer the question? That can be answered based on cost. So if you observe the cost, don't compare this cost with D. They are not checking to compare it with D. They are asking to compare it with the main model. The main model's cost is 77,000. But here the cost is 73,000. So this is more profitable. So yes, you can increase the capacity to 500 and the cost to 443. Even then, you are getting a cheaper cost, and still you are satisfying the demand. Then this part is over. Again, F, you have to check it with the main model. Don't proceed from this model, don't answer F. Then the F question is, if any of the customers' demand, now they are coming into demand, of pure iron will increase, how will it be treated and what will be its implication? Now, if you check in the main model, I have said, the A, B, C, these three are binding. There is no more leeway to do it. But at the fourth mine, you have some leeway. That is 490 minus 240. 490 minus 240, which is 50, 250. But this 250 is not pure. What is pure of it? This into 0.3, which will be around 1575 tons. 75 tons of pure iron can be supplied from mine 4. So now let us go back to the question. They are saying, any of the customers' demand of pure iron will increase, how will it be treated and what will be the implication? The mine 4 has a slack of 75 tons of pure iron because customer only comes for pure iron. He is not bothered about ore, what is the purity and all. So 75 tons can be satisfied. Beyond that demand, as per the main model, you cannot supply to the customer. Only up to the demand can be supplied. That is your answer. Then what is the implication of reduced cost in LP? LPP model. Reduced cost means the coefficient. The coefficients are reduced. What will happen is the question. If the cost is reduced, the optimal solution will vary. But here you can extend the answer as per the sensitivity analysis. The cost is reduced only one, when only one coefficient, when one coefficient is changed within the allowed limit, allowed increase and decrease. Then what happens? Then optimal solution remains the same, but total cost will change. We don't know will it increase or decrease, but it will change. If two or more are changed, two or more coefficients are altered within the increase and they satisfy the 100% rule, then optimal solution remains the same and total cost will change. So if not within the range or if not satisfy 100% rule, then we need to generate new model to solve the constraints. That will be our extended answer to the question. So I hope this case is clear. We'll see the transportation and transshipment in the next video.